Netflix streams over 250 million hours of content times daily. That's a massive API challenge. Here's the secret. Choosing the right API style dramatically impacts performance and scalability. By the end of this video, you'll know exactly when to use REST, GraphQL, or gRPC for your next system design interview. Remember that 250 million hours number. We'll see why it matters when we discuss scaling. We'll also see how the choice of API impacts the cost of infrastructure. Now that we understand the scale, let's define the scope. We're designing an API for an e-commerce platform. Functional requirements: browse products, add to cart, checkout, manage orders. Non-functional requirements: low latency, sub 500 milliseconds, high availability, 99.99%, security, OWASP compliance. Clarifying questions: mobile app support, third-party integrations, payment gateway integration. We'll assume mobile and third-party support, but defer payment details for now. Security is paramount, so we will implement authentication and authorization using OAuth 2.0. API discoverability is also important, which is the ability for clients to easily find and understand the available API endpoints and their functionality. This is crucial for third-party integrations. This sets us up for back-of-the-envelope estimation. Let's assume 1 million daily active users. If each user makes 10 requests per day, that's 10 million requests per day, or roughly 115 requests per second, QPS. 10 million requests divided by 24 hours times 3,600 seconds per hour equals 115 QPS. If each request is 1 kilobyte on average, we're looking at 115 kilobytes per second of bandwidth. For storage, if we have 1 million products with 1 kilobyte metadata each, that's 1 gigabyte of product data. Each order might average 500 bytes, and with 10 million orders per day, that's 5 gigabytes of new order data daily. These estimations will help drive our architectural decisions. We also need to estimate the number of concurrent users, which will impact our server capacity planning. If we assume a peak hour traffic of 10x the average, that's 1,150 QPS. This is where most engineers go wrong. They underestimate peak load. With the foundation in place, let's tackle the high-level design. We'll use a microservices architecture with an API gateway to route requests. We need to consider REST, GraphQL, and gRPC. REST follows resource-based URLs and standard HTTP methods. GraphQL allows clients to request specific data, avoiding overfetching. gRPC uses protocol buffers for efficient serialization and is ideal for internal communication. For our e-commerce platform, we'll use REST for public APIs, product catalog, checkout, because of its simplicity and wide adoption. For internal microservice communication, order processing, inventory management, we'll use gRPC for its performance benefits. GraphQL could be used for mobile clients to tailor data fetching, but adds complexity. We use REST because it's mature and integrates easily with existing systems. We considered GraphQL for public APIs, but the added complexity wasn't justified for our initial requirements. We'll use an API gateway to handle authentication, authorization, and rate limiting. The API gateway will also provide a single entry point for all API requests. Here's the twist. The choice of API gateway is crucial for security and scalability. For example, we can use Kong or Tyke. An example API endpoint would be post API v1 orders, product ID, quantity, user ID.
Here's where it gets interesting. For REST, we must adhere to REST constraints, including HATOAS, hypermedia as the engine of application state. HATOAS allows clients to discover API endpoints dynamically, improving decoupling. However, it can increase response size and complexity. For data serialization, we'll use JSON for REST and protocol buffers for gRPC. JSON is human-readable, but less efficient than protocol buffers. Error handling is crucial. We'll use standard HTTP status codes for REST, 200 OK, 400 bad request, 500 internal server error, and gRPC status codes for gRPC. Performance considerations. REST can suffer from overfetching and multiple round trips. GraphQL can solve overfetching, but introduces complexity in resolvers. gRPC offers high performance due to binary serialization and HTTP2. The mistake most candidates make is not considering the N+1 problem in GraphQL resolvers, where fetching-related data requires multiple database queries. To avoid this, use data loaders to batch and cache database requests. Your interviewer will push back. Why not use GraphQL everywhere to avoid overfetching? The reason is that GraphQL adds complexity and overhead, especially for simple APIs. REST is simpler and often sufficient. We also need to ensure impotency for critical operations like payment processing. This means that multiple identical requests have the same effect as a single request. We can achieve this by assigning a unique ID to each request and tracking processed requests. We can use a token bucket algorithm for rate limiting to prevent abuse. The token bucket algorithm works by adding tokens to a bucket at a fixed rate. Each request consumes a token. If the bucket is empty, the request is rejected. We can also use a leaky bucket algorithm, but the token bucket algorithm is simpler to implement.
The next piece of the puzzle is the data model and API versioning. For our product API, we'll use semantic versioning, v1, v2, v3. We'll include the version number in the API path, /API/v1/product. Evolution strategy. We'll use backwards compatible changes whenever possible. For breaking changes, we'll introduce a new API version. Pause and think. What happens when we deprecate an old API version? We need to provide a migration path for clients and eventually retire the old version. This requires careful planning and communication. We will carefully document versioning policies so that developers know how to use our APIs. We also need to consider data consistency. We'll use eventual consistency for product catalog updates because immediate consistency isn't critical and would impact performance. We'll use a database like Postgres because it supports ACID transactions. Postgres was chosen over MongoDB because ACID transactions are important for financial data. Having locked down the data model, we need to address scaling and performance. We'll use caching to reduce latency and database load. We can use a CDN to cache static assets, images, CSS, JavaScript. For dynamic content, we'll use a cache-aside pattern with Redis. Remember those 250 million hours streamed daily? To handle that volume, we need to shard our database horizontally. We'll shard by product category using consistent hashing. Consistent hashing ensures that data is evenly distributed across shards and minimizes data movement when shards are added or removed. Replication is also crucial for high availability. We'll use read replicas to offload read traffic from the primary database. Bottleneck analysis. The database is likely the bottleneck. Caching and sharding can help alleviate this. Your interviewer will probe what happens if the cache goes down. We'll fall back to the database, but latency will increase. That's why we need to monitor cache health and have a plan for cache failures. To handle reconciliation of data inconsistencies, we can use a background job that periodically compares data between the cache and the database. We can use Paxos or Raft for distributed consensus, but these are more complex to implement. That said, there's a hidden problem here: reliability. Fault tolerance. We'll use multiple availability zones to protect against regional outages. Monitoring. We'll monitor API latency, error rates, and resource utilization. Alerting. We'll set up alerts to notify us of any issues. For example, if API latency exceeds 200 milliseconds, we'll trigger an alert. What happens when a microservice fails? We'll use circuit breakers to prevent cascading failures. The key is to design for failure and have a plan for recovery. We need to monitor service health and have automated failover mechanisms in place. We'll use Prometheus for monitoring and Grafana for visualization. We'll use a service mesh like Istio to manage service-to-service communication and provide features like traffic management and security. Istio uses Envoy as a proxy. In summary, we designed a scalable and reliable API for an e-commerce platform. We chose REST for public APIs and gRPC for internal communication. We used caching, sharding, and replication to improve performance and availability. The main trade-off is complexity. GraphQL offers flexibility but adds overhead. Bottlenecks. The database is the most likely bottleneck. Next steps: implement the API, deploy it to production, and monitor its performance. This is how you design APIs at scale. We chose REST over gRPC for public APIs because REST is more widely adopted and easier to integrate with existing systems. But the trade-off is that REST can be less performant than gRPC. Remember that choosing the right API can save millions in infrastructure costs.
If you found this helpful, please like, share, and subscribe for more technical deep dives like this.